This Mini ITX motherboard has 6 computers on it. And if I flip it over, there are 6 SSDs on the back. What time is it? It's clustering time. This is the Super6c, a Raspberry Pi cluster board. Like the Turing Pi 2 supercomputer I built last year, it fits in normal PC cases. But unlike the Turing Pi 2, it holds 2 more Pis, it fits inside a 1U enclosure, and you can buy it right now for $200. A lot of people test out things like Kubernetes or K3s on a little cluster like this. But today, I'm going to explore something a little different. I'm going to test this thing by turning it into a Ceph storage cluster so I can pool together all these NVMe drives. And we'll see if it can even play in the same league as a $12,000 Ceph storage appliance. Spoiler, it can't, but we'll get to that. I bought my Super6c from DWM Zone, but DeskPi also sells it on their website. It comes with a 100-watt power adapter, some standoffs so you can run the board without a case, and a set of screws to mount up to 6 M.2 SSDs on the bottom. There are spaces for up to 6 Raspberry Pi Compute Module 4s. That's this little guy, which is an entire computer that's smaller than a playing card. And the Super6c has a built-in gigabit switch. Now, that doesn't take all the Pis and put them together and make one giant Pi. You still have to manage the Pis yourself. It's just this board makes it a lot simpler since you wouldn't need to buy 6 Pi 4s, 6 power adapters, 6 Ethernet cables, and a separate network switch. That's how I built my Raspberry Pi Dramble cluster back in the day, but after using this board, I don't think I'll ever go back. This board is truly a cluster in a box, and it's super thin. I'm going to install it in this tiny PC case, and I also designed an I/O shield. Actually, I had to design 4 versions before I could get this one that fit, because the tolerances for some of the ports are a little off. While we're looking at the ports, I guess I'll talk about I/O. There's the power connector that accepts 19 to 24 volts, and I'll talk more about power consumption later. There are 2 gigabit Ethernet ports connected directly to this Realtek Ethernet switch chip, which connects through to each Pi at a full gigabit. Then there are 2 HDMI ports, a micro USB port, 2 USB 2.0 ports, all connected straight through to CM4 number 1, meaning you can manage this entire cluster standalone if you plug in a keyboard, mouse, and monitor. Finally, on the back, there are these 6 green LEDs, and they show you the activity for each Pi in the cluster. But if you like LEDs, that's not all you get. Each Pi gets its own set of 4 LEDs, 2 for power and activity and 2 for Ethernet. Each Pi also gets its own little micro SD card slot on the back, which is useful if you have light compute modules. And each Pi gets its own micro USB port on the top side for flashing modules with eMMC storage. The board has its own little PMU, or power management unit, and it comes with a power and reset button over here. You can also plug in front panel connections, but I noticed the power LED and any fans you have plugged in are always on. That means it can be hard to tell whether the cluster is running if you have it installed inside a case. But you can turn on the cluster by pressing the power button, and you can force shut it down by holding down the power button for 5 seconds. I asked DeskPi if their board's firmware is open or if they have any remote access features planned, but they said no. Also, the onboard Ethernet switch is not managed, so you can't do things like set up VLANs or do any other advanced routing. And no, just plugging in 2 connections to a gigabit switch won't double the bandwidth to this board. I actually tested that. Both of those features are coming on the Turing Pi 2, so with all these kinds of boards, there are always trade-offs. I mean, looking at the board space, I can understand. Trying to cram every feature possible for 6 computers on a Mini ITX motherboard is pretty much impossible. So I plugged all the Pis in on the top, but I couldn't use the heat sinks I normally use, so for now I popped them off and mounted a big fan to the case. I actually started with a Noctua, but even with its quiet adapter cable, it was a little bit loud. Since this board doesn't have PWM, I swapped in this Arctic F12 Silent. It was almost silent, and everything stayed cool even without heat sinks. On the bottom, I installed 6 of these. These are Kioxia XG6 NVMe SSDs, and they're overkill for a Raspberry Pi, but since I had a couple on hand already, Kioxia reached out and sent 4 more. So if you see the includes paid sponsorship thing on this video, that's why. They didn't pay me, but they did send me 4 SSDs to fill up the rest of these slots. After I put the drives in, I flashed 64-bit PiOS to 6 microSD cards and put 1 in each slot. When I flashed the OS, I made sure to add host names like DeskPi 1, DeskPi 2, and so on. That way, when it comes time to connect to them, I don't have to figure out their IP addresses. I think if I had one major complaint about the hardware, it's how hard it is to access the microSD card slots. They're all at different angles, and since they're flat against the bottom, I can't even fit my fingers in to remove a card. A couple times I even had to use a spudger to get my card out. But now, with everything put together, it's time to mount this thing in my case. I found this cheap Mini ITX case on Amazon, and I'll put a link to it below. I slipped in my 3D printed I/O shield, put in the motherboard, and screwed it in. I plugged in the front panel connectors, but then when I went to plug in the front panel USB 2.0 plug, I noticed the header on the motherboard had all the pins on it. It's supposed to be a keyed connector with one pin missing, so I couldn't plug in the USB connector. I also asked DeskPi about this, and they said that this was a problem with the first production run, but it's been fixed now. So, on to the first boot. When I plugged it in, the front panel power LED lit up, and the fan started spinning right away. It looks like those are just always on. When I pressed the power button, all the Pis lit up almost at the same time, and it was kind of fun and mesmerizing watching all the blinking activity LEDs on the back. It reminded me a little of Whopper from the movie War Games.
The Whopper spends all its time thinking about World War III.
I also measured power consumption and found that the board uses less than a watt powered down with just the fan running, about 17 watts with 6 Pis running, 24 watts max, and 11 watts if you shut down the Pis but don't power off the cluster using the power button. One thing I don't like about the design is how the Ethernet ports on the back don't have status lights. I had to check the other end of the cable on my switch to make sure it was actually connected. But everything booted up great except for one of the CM4s had a bootloader issue, which meant its activity LED would just light up green and it wouldn't boot. After a quick trip over to my Pi tray to reflash the Pi's firmware, I got it booting too. And a few quick notes about board power. It doesn't look like there's a way to just shut off power to one Pi at a time, so hot swapping Raspberry Pis doesn't seem like a very safe thing to do on this board. On the Turing Pi 2, it has more advanced firmware, so you can control power to each slot. That's not a huge issue here, but it is something to be aware of. And you know how I mentioned this board doesn't just take 6 Raspberry Pis and slap them together into one big Raspberry Pi? Well, the natural question then is, how am I going to manage 6 Raspberry Pis? Well, you could log into each one with SSH, but in my case, I'm going to use a tool that's perfect for managing a Pi cluster, Ansible. I have a whole book and even a YouTube series on Ansible, and I'll link to them below. But to get started, all I need to do is create an inventory file to tell Ansible where to find the servers. That's this file here. And then a playbook to tell Ansible what to do with them. I won't get too deep into it here, but I've posted the entire playbook in a more detailed guide on my GitHub, so check the link below. The first thing I wanted to do was make sure all the Pis were up to date running the latest version of Raspberry Pi OS. So I wrote this playbook and ran it on the Pis. It updates them all and automatically reboots them if they need to. Then I wanted to try out some software I've never used before, Ceph. Ceph is a distributed storage system. You might know RAID, where you can plug multiple hard drives into one computer and mash them together for redundancy or performance. Well, Ceph is like that, but instead of multiple drives on one computer, you can put multiple drives from multiple computers together in a storage array and let Ceph deal with redundancy and networking. I followed the instructions from this blog post and used a tool called cephadmin to set everything up. First, I just tried installing cephadmin, but apt said it couldn't find it. I actually had to turn on the unstable Debian repository. Since cephadmin is so new, it's not in the repos that ship with the Raspberry Pi yet. But I did that, updated apt cache, and installed cephadmin without any problems. Then I ran this bootstrap command, and to get the cluster set up, I had to know the Pi's IP address, so I hopped over to another terminal and grabbed that. It took about 5 minutes, but at the end, it spits out some information for accessing the Ceph dashboard in a browser. Before doing that, I had to copy the Ceph public key from the main Pi to all the other Pis. But I didn't have that Pi set up to log into all the other Pis yet, so I decided to just do all of it in Ansible, since that would make the process easier. So I wrote this task that saves the public Ceph key from the main server, and then this task that tells Ansible to add it to the authorized keys for the root user on all the other Pis. This way, Ceph will be able to manage all the other Pis when I connect them. And it was a good thing I was using Ansible because I realized after I logged into the dashboard that you had to have some other stuff installed too before Ceph can work on all those Pis. It was saying it needed a container engine and also something called lvcreate, which is part of the LVM2 package. So over in Ansible, I added this task that makes sure Podman and LVM2 are both installed on all the Pis. Alright, with all that done, I could add all the hosts. It took a few minutes for Ceph to get them all healthy, but after 5 or so minutes, they all showed up, and Ceph could tell me how much raw storage was on each Pi. Looking over at the main dashboard, the cluster status was now okay, and it showed the total raw capacity available to Ceph is 3.3 terabytes. Not bad. I wanted to get NFS working so I could test everything from my Mac on the network, so I tried that, but I kept getting this error. I even tried installing some missing packages, but with that, it still wouldn't create the NFS service. So instead, I set up a local storage pool and ran benchmarks using Ceph's built-in benchmarking tool. Write speeds were around 70 megabytes per second, and read speeds were around 110 megabytes per second. That's better than I thought I'd get. In fact, that's about how much speed I could get through a gigabit network, so I'm not really disappointed. Encryption or other fancy features will slow it down, but getting 110 megabytes per second on a Pi is pretty decent. And you might be tempted to think just plugging in 2 Ethernet cables into the board will double the network bandwidth, but it just doesn't work that way. Since the switch on the board isn't managed, you can't configure anything like link aggregation. So at best, it'll just provide a redundant network path. I actually tested this out, and the total speed when running iPerf between my Mac and the board, no matter how many Pis I connected to, always maxed out at 1 gig. And to prove it's not just a weird networking issue on my Mac, I even ran a benchmark across 2 switches to 2 computers simultaneously, and total throughput was always under a gigabit. In fact, sometimes the network performance was a little worse, and I wonder if the switch chip might have been overheating a little. It only got up to about 50 degrees Celsius in my thermal testing, but maybe it doesn't like that much switching, not sure. So after all that, could this thing replace a $12,000 enterprise storage appliance like the Mars 400? In a word, no. And there are 2 main reasons for that: networking and the I/O limitations of the Raspberry Pi. The Mars 400 has less memory and fewer CPU cores, but it has faster internal Ethernet connections plus 4 10 gigabit uplinks, so this thing could pump through gigabytes per second. The Pi can't really touch that, especially since the Super6c can only put through 1 gigabit over the network. So this board is an interesting one. The Turing Pi 2 is a very different product. It has managed Ethernet, so you could assign VLANs or set up link aggregation. This board has a dumb switch, so having 2 ports on the back isn't actually all that useful. The Turing Pi 2 can work with other form factors like the Jetson Nano. The Super6c only works with CM4 compatible boards. And the Turing Pi 2 has other neat tricks like mini PCIe slots, which I used to build a remote 4G Kubernetes cluster that I ran out on my cousin's farm. So both of these boards have their virtues, but I think the biggest thing going for this board is how thin it is and how it crams 6 CM4s on one board. It can be very useful for experimentation or even for some types of edge computing. Oh, also, you can buy it right now and you don't have to wait for a Kickstarter. Assuming Raspberry Pis ever become available again, I think this board would be ideal for doing things like learning Ceph or Kubernetes or other clustering tools. It's certainly a lot less hassle than putting together separate Raspberry Pis, power supplies, Ethernet cables, and a switch. If you want to pick one up, check out the link in the description. I've also linked to all the other parts I used in my build and all the guides and code used in this video. Until next time, I'm Jeff Geerling.